Okay, I have your exams. I just need to enter the scores. So when I put you to work today on something, I'll get those entered and then give your exams back. So let's talk about what? Population proportion, right? Population proportion. So when they take polls, you'll see them in the newspaper, you see them on the internet. Take polls. This is exactly what we were talking about on Monday. So let's take a look at this. So here's some polls about the Democratic presidential nomination. I gave a shout out to Donald Trump on Monday. So let's give some time to Ms. Clinton. So here's a poll. Let's see here. This one. Saying that they sampled 505 likely voters, LV, likely voters, okay? The margin of error for the poll was 4.4. We know what that is. Clinton, 54%. So instead of, so then we'll look at our P as going to vote for Clinton versus not going to vote for Clinton, right? So that's because with our population proportion, we know that it's one or the other. Just there's two possibilities. So we'll say Clinton and non-Clinton. So can you first of all, can you make the 505 likely voters they sampled, the margin of error of 4.4? They say Clinton got 54% of, I guess 54% of those sampled said they were going to vote for her. So can you make the confidence interval? So can you make the confidence interval with that information? Right there. So what is the 505 in terms of the things we've been talking about, the 505?
Sample size?
And yeah, exactly. And that sample size is, what do we call the sample size? N, right? So our N is 505. MOE, 4.4, what do we call that? Capital E, right? That's the margin of error. It's the margin of error. Okay, and then so this is Clinton, 54. What do we call that? What do we call that, and what's the value? What's that? Sample, it's not a mean, but yeah, it's from the sample. What's it called? Sample. Is it P hat? And what's that called? The sample. That's what this whole thing is about. Proportion, right? So we're not doing a mean anymore. It's not like we're taking a bunch of values and finding the mean. We have the proportion of all of the observations that were favorable to something, right? Or favorable to something, or so P hat equals 0.54. Sample proportion. Okay, so can we make the confidence interval?
The margin will be 4.4%.
Yes.
So it'll be 0.
Yeah, we could. It might be easier just to do 54, right? So we can just call it percent, and so just stick with 54%, right? Those mean the exact same thing. 0.54, 54% mean the same thing. So what is the confidence interval for this poll? The confidence interval for this poll. What will we do?
You add and subtract the E from the N?
Yeah, I mean, this in the past, in all our problems, we would calculate this, right? We would do some math to get this. Well, they're just giving it to us, and that's how much we're going to go up and down from the population proportion to get the max and min. Okay, so the center of the confidence interval is 54%. The top is 58.4, right? And then 50.4. So that's the confidence interval that they're. Okay. I just wrote down what someone said and didn't think about it.
49.6.
I was just testing you. Okay. 49.6. Okay, but so then what's kind of missing here? What don't we know? Okay. But regarding this confidence interval, I mean, so what can you interpret that confidence interval? What does that confidence interval mean? Yeah, so we don't know what percent. So we have a margin of error, but we don't know to what percent confident we are that we're between 49.6 and 58.4. So let's kind of try to figure out backwards what that is. Let's try to figure. So we're going to have to kind of work backwards. And so the first thing is, can we figure out what is, how do we get E? E is, it's some number of standard deviations, right? Times whatever the standard deviation is, right? Did we use the z-tables for these confidence intervals? Is that what we did? Yeah, we said for large samples, we use the normal distribution, right? Okay, so we got 4.4 equals, and so what was the, how do we calculate the sigma? What was sigma? What was our standard deviation that we used? We got my symbols backwards here, but yeah, sigma for p hat. What was sigma for p hat? No one has that in their notes?
Square root of
Oh.
p times 1 minus p divided by n.
Okay. We get that? We can get that, right? So find that. As soon as you get it, shout it out and we'll get confirmation on that. As soon as you get it. Now you're going to have to use 0.54 for this. Okay. Someone got 0.022. Someone else get that? Okay, so what's that? 0.11. What the rest of you got? 2.2? 2.2. Okay, so something's wrong with the punching. Okay, so remember our margin of error then is going to be some number of standard deviations times the standard deviation. And that margin of error was? So we got to be consistent now. Now that 0.022 came from the decimal version, right? So this is going to be 0.044. So we can now figure out what the number of standard deviations is. So we're going to take 0.044 and divide by 0.022. Well, that's 2. Yeah.
Why? Okay, so I thought we changed the 0.54 because it was percent, but why is the E a percent?
Because we're adding, right? So we're adding plus or minus to that, right? So it's how much we're going up from the center. So it's the same, has the same unit. Do we get 2? Okay, so now what are we going to do? So z of alpha over 2 equals 2. So what are we going to do? What is that? That's a z-score. And what do we want to try to figure out? So do you know how to use your table to get that? That's a z-score. That's a number of standard deviations. And that corresponds to some area, right? So is 2 an area under the curve, or is 2 a value on this axis?
The area is a curve.
What's the total area under the curve? 1, right? 100% probably. So this is a number of z's are a number of standard deviations away from the mean, right? So this would be 2 and -2. So to build this confidence interval, they're going 2 standard deviations above and below the mean. So how do we figure out what percent confident that is? Look at your chart, and what do you say for 2? What do you get? 0. Which tells us what? Yeah, what area is that? Starting from where, going to where? From the 2 all to the left. Is that what we want? Okay, subtract from 1. And what do you get when you subtract from 1? 0.0228. Okay, that means this area is 0.0228, right? And this one is 0.0228. So what is alpha? So the area to the left of -2 and to the right of 2, they're both 0.0228, right? So what is alpha?
Is it 0.0228 times 2?
Yep, right? Alpha is the total area outside of that. That's right. And what's that? 0.0456. We're getting close. So what percent confidence interval is this then? So all the area outside the confidence interval is 0.0456. Therefore,
Is it a 5% confidence interval? 4.5?
so we're 5% confident
Oh.
that is that right? We're 5% confident that the population proportion is in that range. Does that make sense? No. We want this percent, right? We want this percent. This is our percent that we want.
95.44.
Okay, how'd you get that?
I subtracted, I took 1 minus 0.0456.
Okay, so 1 minus 0.05456 equals 0.9544. So it worked. So when they said the margin of error was 4.4%, they're saying that what? So what's the overall conclusion that we have here? Okay, so we are 95%. We are 95% or 0.4% confident that somebody else. We're 95% confident of what?
Between 49.6 and 58.4% of people voted for Hillary Clinton.
We're going to, yeah, likely voters. From between 49.6 and 58.4% of likely voters are intending to vote for Hillary Clinton. So these polls that you see, and they say the margin of error, this is the percent voting for Clinton, and the margin of error is such and such. Now you know exactly what that means. That's exactly what we did on Monday. Except in all the problems we did, it was you start with how confident you want to be, and then you figure out the confidence interval from that, and find out the margin of error. So in the poll, they give you the margin of error, and so we went backwards and figured out what percent confidence they were basing that on, right? What percent confidence they were basing that interval on. So we always went this way, right? And so now we just went backwards. But all principles that you should understand and be able to do. Okay. Any questions? Okay, so for Sunday night, you have this chapter 11, the stuff we worked on Monday, and then we're going to do section from chapter 12. So you actually have 2 separate assignments. So make sure you know that there's actually 2 different MyStatLab assignments that are due Sunday night. So will be. So one of them's up now. I'll put the other one up later today. Okay, questions on that? Okay, so let's go on to chapter 12. Okay, so chi-square. So chapter 12 deals with the chi-square. So first we got to talk about what is the chi-square distribution. So we've really focused a lot on things that are normally distributed. You're all familiar with the idea of the bell-shaped curve. We've been drawing lots of bell-shaped curves, but there's lots and lots of other distributions of variables that are not normally distributed. And so a familiar one is chi-square. It's not a normal distribution. So let's talk about a variable of number of people in line at Starbucks. Say at any given time. So like throughout the day, periodic intervals, we're going to go, how many people are in line? We're going to write it down. And then we're going to wait a little bit. We're going to say, how many people are in line? We're going to write that down. And then we're going to wait a little bit. We're going to say, how many people are in line? We're going to write that down. This is a random variable, right? This is a random variable. So if I was to sketch the distribution of this, what kind of numbers would I put on the horizontal axis here? 0.1, 0.2, 0.3, 0.4, 50, 100, 150, 200. Okay, so what would be an appropriate scale? Where would I start? Start at 5? Is that appropriate? Go 5 and go up from 5? No. We want to count for all possibilities.
You start at
We're
0.
going to start at 0, right? We're going to start at 0. And then we're going to go up by tens? 20, 30, 40, 50? What should we go by, right? So this is going to be measurement of our variable here in this. So what should I go? So can we get one person in line?
Yes.
Yeah, right? So we want 1. Something like this.
So even if you went up to like 500, you can still do it. Like each
What's that? Yeah, so yeah, I mean, we're probably not going to have more than 30 people in line, and so we could just go like this. So then, what do you think this distribution would look like? So what would this distribution number of people in line? If we just on periodic intervals, we write down how many people are in line. We do that every say 5 minutes or every 1 minute, whatever, and then we gather all the data and we get the frequencies and we make the distribution. So what will that look like?
we'd have to like put in that.
So what would the distribution look like?
Normal distribution, or because like I've never seen more than like average. I see like maybe 4 people.
Okay, average 4. So normal like this? Well, how would it be different than normal? So maybe 3 to 5 is going to be the most frequent, which is let's suppose, right? Something like that. It's going to be the most frequent. So that's where the curve will be the highest, right? But will it be normal like that? What would you expect?
Is it wavy?
Wavy? No.
Is there any reason it wouldn't be a bell curve?
All right, so maybe let's not do Starbucks. Let's do what would be something that would be better? Starbucks is like so Starburnt coffee. Not as popular, okay? Starburnt coffee. So what about that? So maybe there's more like, normally there's 1 to 3 people in line, okay? But people love their coffee, so they even buy it at Starburnt, okay? So like 1 to 3 people. So it's gonna be a normal distribution like this? Skewed. Right skewed. So it's gonna be like this, maybe. We're gonna have the concentration of our observations are gonna be down around some most frequent, like 1, 2, or 3. Sometimes there's gonna be 6, 7, 8 people in line, but not very often. So this is kind of is not a normal distribution. We've got a lot higher concentration to the left, so it's kind of right skewed. It's right skewed. Okay, another possibility is like the total number of runs at the end of a baseball game. What about that? It's kind of similar, right? So what about, could it be 0?
Yes.
Total number of runs at the end of a baseball game?
Oh, no, that can't be 0.
It can't be 0 because they just keep playing innings until someone scores and wins, right? So it's not going to be 0. But what? So like, what is typically the total number of runs by the end of a baseball game? You know, each team scores usually what, like 2 to 5 runs. So maybe, you know, maybe the total like around 5 is the most frequent. So we're gonna see some games with just 1-0. More games are gonna have 2 total runs, 3, but like the most is gonna be like maybe this, and then, but then there could be there could be games with big scoring, lots of scoring, and the total runs is high. But I shouldn't have done it this way. It's not. So it's not a bell curve, right? So it's like this, and then swooping down like this. Okay, so this is not. There are variables in the world, but I'm trying to tell you that are not normally distributed. Okay, there's a much bigger concentration of frequency on at the left end for lower values, and then higher values are possible, but not as likely. So this is an idea of the chi-square distribution. So here's the properties of a chi-squared curve. Chi-square. So chi is the Greek letter. It looks like an X. And so the total area under the chi-squared curve equals 1, just like our normal distribution. The chi-square starts at 0 and extends indefinitely to the right. So it starts at 0, extends indefinitely to the right. The chi-square curve, like you guys said, is right skewed. It's right skewed. Because of the high values that are possible, it pulls the mean to the right.
So it's always going to be right?
Always right skewed. It always looks like this. Like the highest frequency is for lower values, but higher values are possible. So it's always right skewed. Okay, and then we have different chi-square curves according to degrees of freedom. Remember we talked about degrees of freedom. With lower degrees of freedom, you have a higher frequency at lower values. With higher degrees of freedom, your central, highest frequency is at higher values. And what do you notice for higher degrees of freedom? What seems to occur? Because looks more normal, right? So for lower degrees of freedom, it's more right skewed, less normal, and then for higher degrees of freedom, it starts looking like a normal distribution.
Is it ever, so it's never normal?
Right, but it approaches normal. So I suppose if your degrees of freedom was like 100 or 200, it would essentially be normal, but it's still not quite. Not quite. It just gets more and more normal for higher and higher degrees of freedom. Okay, so that's the basics of the chi-squared term. So we're going to use chi-squared to do what's called goodness of fit. Goodness of fit is what we're going to use the chi-squared for. So here's frequencies of last year's violent crime distribution based on the 2000 distribution and 500 total crimes committed. So unfortunate reality in our society that we have violent crime. Okay, so based on 2000, so where do these numbers come from? For 500 out of 500 crimes committed, based on 2000, they would expect 500 or 5 out of 500 would be murders, and then 31.5 of the 500 crimes would be forcible rape. 143 of the 500 robbery, and 320 out of the 500 aggravated assault. So this is what's expected. Expected number of crimes in each category if you had 500. So here's what we're going to do. We had the expected, that's what we just looked at. And then this is observed. Okay, so these are observed, so this is expected based on the year 2000. And this is, say, observed in some later year. Say, observed in, we'll just make it up, in 2010. So there were actually 3 murders, actually 37 forcible rapes, 154 robberies, 306 aggravated assaults. Based on the 2000 data, this is what we'd expect. So what we're going to look at is we're going to say, we're going to do a test, a hypothesis test, and we're going to say, based on the evidence, is there evidence to suggest that the observed frequency is different, this distribution of these 4 is different than the expected, or is there not enough evidence to say that this observed frequency is different from this? So we want to know, is what we expect, what we're still seeing in the current state of things, or is it starting to change? Right? Is something we're doing in our policies making the observed frequency change from what we expected based on what happened before? So how are we going to do that? We're going to look at the difference, right? So the difference is how much possible change there was. So we're going to do O minus E. O minus E is the difference between the observed and the expected in each category. Okay? And then we're going to square that number. And then we're going to divide by the expected in each thing. And then we're going to add all those up. So and then we're going to get a number. And this number is a measure of, as a whole, how different the observed frequencies are from the expected frequencies, right? Because as this O minus E, as these deviate away from E, these numbers will be bigger. So these numbers will be bigger, and so this sum total will be bigger. So this is a measure of how different the observed is from the expected. So it's a single number that's indicating how different the observed was from the expected. If this number is bigger, then we're seeing more deviation away from the expected frequencies in our observed. If this number is smaller, then it's lining up more closely with these expected frequencies. Does that make sense? Why? Because how's that number calculated? It's basically it's a way of calculating the total difference, right? So we take the differences, we square them, we add them up. So the bigger that number is, the bigger these numbers were, or how different O is from E. So this is the variable. This is the variable that we're gonna have be our chi-squared variable. This number that's indicating how different the observed frequencies are from the expected frequencies. So this is our random variable that we're going to use the chi-squared test for. So let's check it out. Okay, so we're going to do the chi-square goodness of fit test. So here's the requirements. All expected frequencies are 1 or greater. At most, 20% of the expected frequencies are less than 5. And we have a simple random sample. So these numbers are getting at, we don't want our frequencies to be too low. You've got to have enough data, right? So this is basically, both this number 1 and 2 are basically about n being large enough. And n large enough in each category. Okay, so here's going to be our null and alternative hypotheses. Null hypothesis, the variable has the specified distribution. So we had that expected, and then we had the observed. And so what we're saying in the null hypothesis is the observed is the same as what we expected. The observed distribution of things is the same as what we expected. And then the alternative is that what we observed is different than the specified distribution or what we would expect. So, in a nutshell, this is observed is equivalent to expected distribution. And then the alternate is the observed is not what we expected. But as we know with these tests, it's not black and white, right? It's just, do we have enough evidence at a certain confidence level, right? So we want to be 95% confident that we're not making a type 1 error. So it's not cut and dry, but we know that our hypotheses are black and white, but our conclusions are not, right? Because it's just based on the evidence that we have. Okay, so we have a significance level, and then we saw in that table, this is going to be the value of the chi-square statistic. This means we're going to add up. We're going to add up all the squares of the differences divided by the expected, and that's going to be the value of the variable. And then that's going to be the test statistic, and then based on our significance level, we're going to compare them and either reject or reject the null or not reject the null. All right, so let's do this first example together. So now, with the frequencies, there's frequency and relative frequency. So we gotta know the difference and know what we're working with. So here, 85, 215, 130, and 70. Are those frequencies, like actually counting number of events? Or are those relative frequencies, like percentages? What must those be? Remember, relative frequency was when we broke all the categories up into percent, right? Or proportion. Observed frequency would just be like you actually counted that many. So which would that be? Frequency or relative? That's got to be frequency, right? These aren't percents. So what was our total number of observations? $500. Okay, so now this distribution, are these frequencies or relative frequencies? 0.2, 0.4, 0.3, 0.1. Right, so we observed 500 times. This is like expected, right? The distribution, expected. Relative frequencies or frequencies? Relative, right? So we need apples to apples here. I don't want to write that down because if we're going to do O minus E, we need those to be in the same unit, right? O minus E have to be the same. So I need to get the frequencies here instead of the relative frequencies. So how would I do that? This is saying 20. So category 1, we expect 20% of all observations to be category 1 type. 20% of 500, right? So you're going to take 20% of 500, and what are you going to get? 100. So the expected number of observations at 20% would be 100 if you have 500 observations. Okay? 40% is going to be, we're going to expect 200, just twice as much as 20%, right? 30%, halfway between those. No calculator needed, right? 150. And then what? 10% is half of 20%. 50. So we're expecting this distribution of our whatever our 4 categories are, 100 of these, 100, 200 of these, 150. Maybe it's like favorite color or something. We're expecting, like blue, green, purple, and other or something. All right, and then we went out and we took data, and we got these numbers for those 4 categories. Now we're saying, is this distribution what we expected or not? At a 5% significance level, is that distribution what we expect? Does it match up with this? Closely enough that we would say we're not going to reject the null hypothesis. They could be the same. Or is this enough different from this that we would say, no, we have evidence to suggest that the observed is different from what we expected. All right, so you're going to finish the table. I'm going to pull the chi-squared table. I forgot to print them out for you. So can you finish the table? So you're going to get the differences, and you're going to square them. Then you're going to divide each one again back by e. Then you're going to sum them up, and that's going to be our test statistic that we're going to use the chi-squared distribution for. We've got 4 categories or possible values of the variable, so your degrees of freedom is 1 less than that. So we're going to come over here, and that's our significance level. So let's draw a picture so we see what's going on here. So we got our distribution, like this, chi-square. And what did you guys get? You did all the math here, and you got a chi-square total. Do you guys agree on that? What did you get for that value?
14.05.
14.05. Did we got a consensus on that? 4 point something? Is it 14 point something or 4 point something?
You got 14.05.
0.05? So this would be, let's see, negative 15, 15, negative 20, 20. So then 225, 225, 400 and 400, each divided by e. So 2.25, 1.125, what's 40 over 15?
Well, it's 2.6666.
2.67 and 8 point something, 8 point. I think the 14s have it. So it's going to be the sum of those. Looks like the 14s have it. So 14.05. Okay, so that's our test statistic. So that's a number here on the chi-square distribution, right? 0 is here, 1, 2, 3, 4, etc. So right here is our test statistic, 14.05. And remember, we said the higher that number is, the more likely that the observed is different than the expected. Okay, so we need a critical value. So the critical value comes from the significance level of 5% and our degrees of freedom, which is 3, 1 less than the number of possibilities for the variable. So we come to our chi-squared table here. So at the 5% significance level, 7.815, right there. Everyone see that? So the rejection and non-rejection region is based on the critical value, okay? So remember, not rejecting means saying there's not enough evidence that these two things are different. These two distributions are different. Rejecting means, okay, there's evidence to suggest the observed is different than E. So is the rejection region going to be to the right or to the left? Remember, the bigger this number, the larger this number, the more possible it is that the observed is different than the expected. So rejection to the right or to the left? To the right. Bigger numbers of this value suggest more deviation from the expected. And so your rejection region is going to be out here to the right because our null is, they're the same. then the alternative is they're different. And so if the bigger the number, the more likely they're different, then that's going to be our rejection region for the alternative hypothesis. So this is our rejection region. And this is the non-reject. So how about for this test? So H naught O is the same as E. Alternative, O is different than E. So we got a chi-squared, based on the data, based on the observed frequencies, we got this number, 14.05, suggesting a level of difference between O and E. So, are we going to reject or not reject the null hypothesis? Reject, right? We're here in the rejection region, right? We're going to reject. This number is significantly bigger than the 7.815, suggesting these observed frequencies are notably different than the expected frequencies for whatever we're talking about. So we're going to reject because there is evidence. Whenever we reject, there is evidence for something. Whenever we don't reject, there's not enough evidence for something. That's always true. It's always true. So we're rejecting because there is evidence to suggest that what?
The observed frequencies are
Different from the expected.
Distribution.
Right. So as a whole, this is different than that at the 5% significance level. And so remember what the 5% significance level meant. It meant that there's a 5% chance of making a type 1 error. If we're out here, there's 5% chance that based on the data, we rejected what we shouldn't have. Remember that? Let's get the actual p-value. So the actual p-value would be for our test statistic would be this here, this area here. So can you figure out what that area there is? That's the p-value. And that's not proportion, right? That was from before. How would you find that p-value then? How would you find that p-value? What would you look at?
The chi table.
Chi-squared table. Where are we going to look? Well, it's going to 3 degrees of freedom is the same. So at a chi-squared value of 14.05, we're asking what area would we have out there to the right that I've shaded in red? So 14, where's 14 in this row? It's off the chart. So the best we have is this one, right? The biggest one we have is 12, and what alpha is that? 0.005, 0.5%, right? 0.00 from the chart, 0.005, or alpha is less than 0.5%. Right? P-value is the area, right? It's the area that we want. We get those up here. So it's going to be even a smaller number than 0.005 because ours is 14. This is as high as we go. 12.8. Right? These numbers are getting greater this way, right? So for 14, it's going to be less than 0.5%. So what does that tell us? It tells us the observed frequencies are so much different than the expected that there's really less than a 1% chance that we made a type 1 error, that we rejected and we shouldn't have. So the bigger this number is, the more confident that these are different. How confident are we now that we didn't make an error? Less than 1% of the time with this kind of data, we would be rejecting incorrectly. We would be saying that they're different when they're really not. So that's a high degree of confidence that these two distributions are different. Okay, did you catch all that? Does it make sense? Somewhat. We need to do some examples. So a really cool aspect of this is like in gambling. Is it a fair game? So let's look at an example here of roulette. Okay, is it rigged or not? That's what this is a perfect test for. Is it rigged or not? So an American roulette wheel contains 18 red. Let's a little bit bigger. Okay, an American roulette wheel contains 18 red, 18 black, and 2 green numbers. So in 200 trials, what would we expect? So what would we expect in 200 trials? How many black would you expect? How many total possibilities are there? 18 red, 18 black, and 2 green. That's 38. So we have 38. And what percent of the time would we expect red? So red would be expected what percent of the time?
18 over 38?
Right, 18 over 38, we would expect that would be the relative frequency expected for red, right? Black, we'd expect what? Same thing. And green? 2 over 38 would be the frequency the relative frequency of green that we would expect. So let's get those as decimals. What's 18 over 38?
0.474.
One more decimal place. Same with black. What about green? 3 decimal places.
0.053.
0.053. Okay, so in 200, so they went to a particular roulette table and they threw the ball 200 times. They spun the wheel, threw the ball 200 times. These were the outcomes. So, is this a rigged table? Meaning, does it favor one color more than it should? So this would be perfect. If it was perfectly random, it would be according to these percentages. So here's the results we got for a particular table. Is it rigged to favor one color over another? Okay, so what did we observe? We observed 88 red, 102 black, and 10 green. How many out of 200 would we expect? So red occurs 47.4% of the time. So how many reds would we expect in 200 throws or 200 spins? What will you do to find what you would expect in 200?
94.8.
Okay, you take this percent or this portion of 200 and you got 94.8. Okay, and then same with black, because they're the same. And then what do we expect for green? How many do you expect to be green out of 200? What'd you get?
10.6.
10.6. Okay, so you guys are gonna do at the 5% significance level. And you have everything you need, right? So you're gonna find the test statistic. So that the table's over here now. You're gonna find your test statistic by building that table. And then you're going to get the critical value based on the 5% significance level, and you're testing to see does the data suggest that this is a rigged table. It's not giving results that you would expect. Or is there not enough evidence to suggest that it's a rigged table? So let's write down the null and alternative hypothesis before you do all the number crunching. What's the null hypothesis? And what's the alternative hypothesis?
Observed equal expected.
And so what does that mean in this situation? Observed equals expected. So can you talk about roulette?
It's not like
The table is not rigged. Alternative hypothesis. Hey, this table is rigged.
This is a really rich gambler.
What's that?
This is a really rich gambler. He could like do the wheel 200.
No, so this was like they had an independent investigator come in
Oh,
and spin it, like in their controlled experiment. We have suspicions. People are accusing you that your table is rigged. So they bring in some independent investigator and they do their 200 trials and they run their stats. But there's lots of rich people in the world anyway. Okay, so you got everything written down? I need to get. What did you find? What was the test statistic? 1.06, something like that. And then what was the critical value? What do we think? Yeah. No, we never accept the null hypothesis. We never do that. What do we do?
there's not evidence to disprove that.
Oh yeah, we do not reject.
Do not reject, right? We do not reject. So is there evidence or no evidence? Or not enough evidence? Not enough evidence to say the table is rigged. Okay, so now to turn in, let's do this next one. Is the die loaded, right? Is the die loaded? So, 4 things, ready? And then I don't have sheets for you, so you're going to have to use your own paper. If you give me a clean left edge, please. Clean left edge. Use your own paper, so do this separately. And we're going to do what? We're going to do state the null and alternative hypothesis.
No, please. Oh, I was just gonna write
Find test statistic and critical value. Conclusion. Statement of explanation. For the dice. This is to turn in. So separate sheet of paper. Give me a clean left edge. Work together. Can you read that? Is it big enough to read? Work together, okay? Did you need the screen?
I didn't take the O's this time. Yeah.
What was the? Does anyone have the table values? Does anybody have the table values? Okay, I want to show you how StatCrunch can do this. So we'll make variable 1 be our observed. What were the observed frequencies for 1 through 6? 23.
26, 23, 21, 31, 26.
Okay, so that was the observed frequencies. And so then variable 2, we can make what would we expect. So in 150 rolls, how many would we expect for the number 1? 1/6 of those, right? We expect 25. What about 2? All of them we'd expect 25. Is that right? Okay, so we're going to go to stat. Everyone watch. Ready? Stat. Goodness of fit. Goodness of fit. Third from the bottom. Chi-squared test. All right. What's our observed? Variable 1. That's what we put in. Observed as variable 1, right? Expected. Now, look, there's an option for the situation that we have. All the outcomes have the equal probability. So instead of doing expected variable, I didn't need that column. I could just do all cells in equal proportion. You see that? But this is fine too. If they're not in equal proportion expected, then you would select the column. But for this one, I could have also just clicked on that. Okay, and then this is a chi-squared test. Variable 1's observed, variable 2 is expected, and then we're going to compute. See if this agrees with what you guys got. Degrees of freedom 5. The chi-square was 2.48. Did someone else get that? Did you guys get 2.48? Awesome. And now, so for 5 degrees of freedom, what did we get for the 5 degrees of freedom and 5% significance? Is that what it said? 11.07. Oh, it's not up there. Shoot, I think it went off. Anyway, so that is, looking at the table, 5 degrees of freedom, 5% significance level, 11.07. 11.07 is our critical value. I don't know what happened to that screen. Shut down. Anyway, you get 11.07. So what's the conclusion? Reject or do not reject? Do not reject, right? Do not reject, because this number is the rejection region would be to the right of 11. And so we're way to the left of 11.07. And so we're going to not reject. And the conclusion is There is evidence, or there's not enough evidence. Not enough evidence. If we're not going to reject, there's not sufficient evidence to say what? The die is loaded and favoring one number more than another. This is perfectly legitimate distribution, rolling the die 150 times to suggest it's a fair die. No, that it's not a fair die, right? There's not enough evidence to suggest that this is an unfair die. It very well could be fair. It very well could be a fair die.